and we'll now move on to our next presenters. So our next two presenters are Rishab Jain and Aditya Jain from Samyak Science Society. So a brief introduction for both of them. Rishab Jain is the co-founder of Samyak Science Society. Rishab is a high school student who believes in the importance of teaching curiosity. His own curiosity has inspired him to develop tools to improve pancreatic cancer treatment, make YouTube videos, and engage in public speaking at TEDx. He has also been named America's top young scientist and one of Time Magazine's 25 most influential teens. Aditya Jain, also the co-founder of Samyak Science Society. Aditya is a senior at Boston University studying biomedical engineering on the pre-medical path. His research focuses on improving cancer screening using artificial intelligence, and he has established 5 papers. Aditya believes that experimental learning will empower youth to pursue STEM. His advocacy efforts have led him to being named a top 30 changemaker by the T-Mobile Foundation. So now I'm excited to welcome Rishab and Aditya to present about their project and their mission.
Hey everyone, we're going to get started in a second here. If I can figure out how to share the screen. There we go. So can everybody see this and hear us all right? Yeah? Okay, so we'll get started now.
Artificial intelligence is to computers as what the microscope was to humans 100 years ago. It has allowed us to do amazing things like design cars, build houses, create music, and even write books. We've even used it in medicine. The first step is for us all to understand how this technology works and why it matters. Today, we are going to learn about artificial intelligence and how it is going to change the world. I guarantee you that what you learn here will surprise you. And the first surprise is that everything you've heard me say so far was written by an AI. Hello, everyone, and welcome to the AI Synapse. Let's get started with today's agenda.
So today we're going to be covering 3 major branches of artificial intelligence. Then we're going to be talking about neural networks and convolutional neural networks. We're going to be talking about natural language processing, which is the sort of tools which allow us to create speeches like what Rishab just said. And finally, we're going to be talking about reinforcement learning. And at the end, we'll recap all of this and talk about how you guys can get involved at the next level and what are the next steps going forward. So starting again, thanks for the introduction. My name is Aditya, and as was mentioned, I'm currently at Boston University. I'm a senior studying biomedical engineering, but I plan to go into medicine. And this is Rishab.
Hi guys, I'm Rishab, and I'm a rising sophomore in high school. Thanks for the great intro. I'm very interested in artificial intelligence and can't wait to get started with you all.
So we're here representing Samyak Science Society. Just a brief introduction to that as well for those of you guys who don't know about it. Samyak Science Society is an organization which sort of believes in sparking curiosity in youth. And we believe in the power of learning through hands-on workshop style approaches, which we call experimental learning. In the past, we've done a lot of these workshops with younger children. And so today we're really excited to be, talking to a bunch of, from what I understand, high schoolers and college students about artificial intelligence and sort of with this same goal in mind of how do we spark curiosity and allow people to really explore STEAM by exploring these areas with hands-on approaches. So with that, let's just get into the first section. We're going to be talking about artificial intelligence and its connection to neuroscience. So artificial intelligence is defined as the capability of a machine to imitate intelligent human behavior. And jumping back, almost 80 years at this point, the idea of neural networks was actually established in 1943, far before we had the ability to actually implement these solutions in real life. After that point, there was a man named Alan Turing, who is, very famous. He's hailed often as the inventor of the modern computer and the idea of computing. He came up with something called a Turing test. And this sort of defined what is the idea of artificial intelligence that we kind of still use today. What he defined as the Turing test was artificial intelligence will be a machine which can convince other humans that it is not a machine, but rather a human that they're speaking to. And so this sort of Turing test has remained kind of a gold standard in artificial intelligence today. After that, growth has kind of skyrocketed. We had the first idea of artificial intelligence and the Deep Blue system, which was able to beat Garry Kasparov, who's a chess grandmaster. And then since then, we've started to venture into deep neural networks, into machines like self-driving cars and technology that we all use every day, like Siri, Google Now, and Cortana, which use other branches of machine learning and artificial intelligence. So with that, there's kind of two main branches of AI. The first is sort of a classical branch, and this is where a lot of the early advancements in artificial intelligence happened. The classical branch kind of states that we can train artificial intelligence through rules. Let's think of a simple problem, like if you had to differentiate a dog from a cat using just your eyes. Well, we kind of know there's certain things about dogs that we've learned over time. Like dogs generally have, longer ears than cats. They have bigger noses. They weigh more. These sort of features can then be encoded as rules. So you could think of a simple system which says, if the object I'm looking at has big ears, if it has a big nose, if it weighs over, a certain amount of pounds, it's a dog. Otherwise, it's a cat. And so this sort of rule-based programming kind of was the original idea for artificial intelligence and fell into this sort of classical strategy of AI. However, as you can sort of immediately see, this approach has a lot of problems and runs into a lot of immediate limitations. If we wanted to do anything complex, like, current tasks of determining if something is a cancerous tumor or not, you would need thousands upon hundreds of thousands of rules, and encoding those all by hand is a pretty much impossible task. So today, this has kind of all changed with the introduction of machine learning, where machines are able to learn rules themselves without us hard coding these rules. And this sort of discipline of modern artificial intelligence has branched out into three major areas, which is what we're going to be talking about today.
So with that, let's get into the neural network. So the neural network kind of reminds us of what the human neuron looks like in our brains and the rest of our body. So I'm sure all of you guys have seen this many, many times in biology class, but let's just quickly go over the neuron. We have our dendrites, which take signals from and take impulses, and we have our soma, which determines if those impulses should be transmitted on. Those are sent through the myelin sheath, and finally we have our axon terminal, and this will result in the signals being put into and getting taken up by other neurons. And this sort of concept has led to the artificial neural network, which was loosely inspired by the human neuron. Rather than just taking in a signal of sort, we can actually take in data, or we can take in other sorts of inputs and run that along the neuron. And finally, we have our output. And this is sort of what a more simple version of the neural network looks like today. We have these nodes that make up the input layer, our hidden layer, and our output layer. And each of these nodes represents a neuron. It takes in an input, and each of these nodes will have a weight and a bias. They will conduct various math and matrix manipulation to get some sort of value, which is then outputted. And finally, in our output layer, we hopefully will do some sort of classification or prediction. And as you guys can see, when we add in a lot more nodes and connect things together, neural networks can get scaled up and become really complex quickly. This is more of a mathematical representation of what the artificial neural network looks like when it comes to training AI. And as you guys can see, there's an input, and this could be in the form of data or numbers. And we have our weights in our neurons, and these are essentially multiplied, and math is done there. And this is all sent to a transfer function, which sums up all of these values together, and we get this sort of net input. Finally, we have our activation function. And some of these activation functions you may be familiar with, things like the ReLU, softmax, and tan. And essentially what the activation function does, it has a set threshold. And if our net input meets that threshold or is above that threshold, it will activate, sort of like how the neuron will determine whether or not to send on an impulse or a signal. So Aditya can tell us a little bit more about where the neural network is actually useful today.
Yeah, so this kind of simple neural network that we talked about has kind of expanded really rapidly as the power of computing has made it cheap enough where we can have not just 5 neurons, as we showed in our last picture, but billions and even hundreds of billions of neurons. And once you have so many neurons together, it's able to do a lot more complex tasks and identify and learn features which are more complex and harder for humans to necessarily interpret. So some examples of where this has been used is in medicine. There currently, there's been a lot of research that's published, and this is one of the areas that I'm actually working on, is for figuring out how do we predict what is a benign or malignant tumor, or how do we get a machine to be able to segment these regions out just using non-invasive CT scans and other forms of imaging. Some other approaches have been self-driving cars. These also use neural networks to be able to classify images that the car is receiving. The car can be mounted with a camera that's facing the road, and then the camera can tell the car, oh, there's a pedestrian in front of me, or this is a bicycle, or this is another car, and we don't have to worry about it. So these sort of decisions are all, kind of based on this concept of the neural network, which we've talked about. And finally, a recent field has been deepfakes. I'm sure many of you have heard of this. It's something that's kind of spouted a lot in the popular media. But deepfakes are fundamentally based on neural networks as well, where the neural network learns to recognize what makes this a face of Obama, or what makes this a face of whoever you want to choose. And then it can generate its own faces in a specific fashion, which mimic that person. So now we want to go into our first workshop. Because of time, we're going to just demo this one, but our future workshops, you guys will actually be able to do it. So let me go into the demonstration for this workshop. I have to exit the screen share for a second here. Just let me do it. Sorry, I need to figure out how to screen share it over here.
I think there's a way where you can, there we go. Yeah, you can screen share the entire screen, and we can see your chart right now.
Okay, can you guys see like us typing and going to the website?
Yes.
Okay, perfect. Yeah, so all of the workshops that we're going to be talking about today, you guys can go to our website, samyakscience.org/neurocon. And that's where these workshops will be hosted. So we're just going to go through one of them. And then in our future workshop, you guys will be doing it hands-on. But we'll just do a quick demo of this to show you guys. This is a website called Teachable Machine. And what Teachable Machine does is it allows you to train a neural network just from your browser. So it hides a lot of the coding, but it allows you to kind of experiment with a neural network. And just as a quick example, we'll go through one of the image projects so you guys can see what this would look like. You would essentially can define multiple classes. So neural networks are really good for classification type problems, as we talked about. And you can take pictures of, maybe one class could be pictures where you're, saying thumbs up, and another class would be pictures where you're doing a thumbs down. And then you train the model, and the model will automatically learn features to differentiate between these two classes. And the really cool thing about Teachable Machine is it'll let you play with some of the parameters which go into training a model, like the amount of time that you want to train it, which is kind of like epochs, how many images it should train on in a single iteration, and how fast it learns. And messing with all of these parameters, which will change the way that your network sort of learns about the problem. So you guys will be able to play with this. And again, this will be on our website, but because of time constraints, we want to move on to our next example here. All right.
So with that, let's get into natural language, which is really interesting. So natural language sort of refers to the everyday communication, the language that we use for that. In this case, it could be something like English. The way that I'm talking to you guys right now, we're using a form of natural language. And this brings up a question. How can we process this language? Well, that's exactly why the field of natural language processing was created, also known as NLP for short. And NLP is basically a section that takes up both computer science and linguistics together. And it often includes the use of artificial intelligence and machine learning. So natural language processing really has two main subfields, which are generation and understanding. So generation is sort of like where we're trying to generate text. For example, at the beginning, when we started our presentation, I started out with that mini paragraph, and that was actually generated by an artificial intelligence model that was using this NLP generation. And then on the other hand, we have understanding, which is sort of where we take our text and we try to understand the meaning of that. And you guys are pretty familiar with syntax and semantics, which are how the words are placed and how they're organized in a sentence versus the meaning behind the words. And the goal of NLP is to have our machine, our model, to be able to understand that. So now we have a question for you. What do you think natural language processing could be used for? It could be either for generation or understanding. Feel free to type some examples in the chat. It could be things like speech recognition or even chatbots. So we want to see what you guys think NLP could be used for. So somebody said it making Kanye songs. And that's actually correct. We're actually going to briefly mention music in a little bit, how music can actually be generated using a combination of neural networks and NLP. Another person said building smart robots. Exactly. So if we have a robot who's talking to a person, for example, even if it's just a voice assistant, it's using NLP. Summarize a piece of text. Exactly. If we have some complex text and we're trying to understand that, NLP could be used. So besides that, NLP can also be used for things like spam detection, identifying parts of speech, sentiment analysis, which is understanding, the meaning behind understanding the meaning of words and sort of the emotions and thoughts they're trying to trigger, text composition, question answering, summarization, which is one of the things you guys mentioned, and then conversational interfaces. So with that, now that we sort of understand what NLP is, let's look at more of a technical aspect, a view of that. So at the beginning, we have our vector, which is called W. And our vector W has different indices, which are defined as words. So we could define a 5-word sentence, and that's stored in our vector W. For example, hello, my name is Rishab. So in this case, we're masking a word. And a mask is basically where we still have the information of what the word is, but instead our computer, our model, is trying to predict that word given the mask. So in this case, our model is trying to predict the word is. Then we have a transformer encoder, which will essentially encode this information that we've just given it. And often there's a decoder step as well. And this will essentially give us our outputs. This is then sent to a classification layer where earlier you guys saw the neural network where we have all of our outputs from the previous step fully connected into the next layer, as well as a GLU. And you guys might have seen the ReLU as well. And that's an activation function that's used for the classification and prediction there. And then finally, we embed this to our vocab and use a softmax layer to get our actual prediction. And here, hopefully, our natural language processing based model is able to predict that word is to get our sentence.
So one of the cool things about natural language processing is that it allows us to create data and problems just from sentences. So in our previous examples of artificial neural networks, one of the main limitations of artificial neural networks is you need a classification already given. For example, when we talked about telling the difference between a dog and a cat, you have to tell the network that these are images of dogs and these are images of cats, so that way it can learn how to solve that problem. With the natural language processing system, however, we just simply mask words from the neural network and have it predict those same words. So it learns text just by looking at examples of text. It's kind of a mix of supervised learning where we give the machine the answer and unsupervised learning where the machine has to figure out something from the data itself. So that's one of the interesting aspects of NLP.
So where is natural language processing really useful? Where we just discussed a few use cases and examples, but again, it could be used in amazing technology like the Amazon Alexa and Google Home. It's even used in things like YouTube. YouTube has to process hundreds of hours of videos every single minute that people are uploading. And they use natural language processing to automatically transcribe the entire video and understand and that's sort of referred to as the YouTube algorithm, to understand what the video is talking about. It can be used for translation tasks where we're taking a word in some language and we're directly trying to translate that into another language. And finally, of course, generating Kanye songs. No, I'm just kidding. But again, it could be used for things like music, which is really interesting. And finally, we also have summarization. So our neural network with natural language processing can actually read something extremely complex. Today, we often just flip through the pages of legal documents and put our signature. But a natural language processing model would be able to understand this text and then sort of give us a plain English response to what that text is. So that's another very cool example.
So now I want to go into one of the topics that sort of relates natural language processing back to neuroscience, and one of the key questions with natural language models is, are we actually approaching an artificial general intelligence? At the start of this talk, I kind of talked about how Alan Turing sort of predicted that if we have a neural network or any type of artificial intelligence which can convince another human that it too is a human, not a robot, just by speaking with it, then that's something which is actually intelligent. So with natural language processing, you can see why people have started to think about this a lot more clearly. Some of the text that it generates, while there's still errors here and there, some of it gets really close to things which a human would write. And so some people have started to wonder, are we really approaching this artificial general intelligence? And one of the theories which has sort of come out of this is the Chinese room hypothesis. So the way the Chinese room hypothesis or thought experiment goes is, imagine you have this, box, and you can't see inside the box, but there's this box, and what it says is, this box will talk to you in Chinese. So you write something in Chinese and give it to the box, and out comes a perfectly written, well-written response in Chinese that answers your question. Like if you say, oh, hello, my name is Rishab, it'll be like, hey, nice to meet you, Rishab. And it's in fluent Chinese. But now looking inside the box, we see that inside the box, it's actually just a man which only knows English, but he has this massive book of rules which tell him how to convert things from Chinese to how to convert a Chinese input into a Chinese output just using those rules. So he doesn't actually understand any of the Chinese. He's just using this sort of pre-built rule book. And that's sort of the comparison that a lot of people draw to natural language processing. It doesn't really understand what we're saying. It's just generating a stream of words which are well matched to the input. But this is just one theory, and there's people aren't really sure about what the answer is here. The other thing that's sort of happening is some of you guys may know about Moore's law and how the compute power in the world is increasing at a drastic rate. And what we sort of found is that some people sort of believe that these sort of natural language processing algorithms would naturally level off, that we'd stop seeing improvement at a certain point because they weren't actually learning human text. They're not smart in any way. But what we found is that as we increase the compute, we increase our amount of data, and we increase the number of neurons, the model's loss just keeps improving at a linear rate, at kind of like a logarithmic rate, really. And so this kind of is sort of leading some credence to the opposite side, that maybe it is learning something more fundamental about language than just inputs and outputs. And as we sort of get today, the biggest natural language processing models have hundreds of billions of neurons and parameters, but our brain has trillions of neurons, tens of trillions. So some people are hypothesizing that perhaps once we get closer to that number, 10 trillion neurons, we might start to get machines which generate writing that's indistinguishable from humans. So now we're going to go into our second workshop, which is called the AI Dungeon Workshop. And this one you guys will actually do hands-on. So first we're going to demo it for you, and then we'll give you guys a chance to do this. So AI Dungeon is one application of natural language processing. And what the AI Dungeon does is it generates text that tries to fit a story. So you can give it any text input and it'll try to generate a follow-up story. So we're going to go here, and this is our website again, samyakscience.org/neurocon. We'll go to workshop number 2, which will take you to the site. And apologies for the slow internet connection, but so we'll click play, new game, single player, and we're going to choose the custom setting. So now what we're going to do is I'm going to edit this here to give it a prompt like this. And our prompt is you are, let me put a name here. So you are Rishab, a noble living in the kingdom of Larion. You have a pouch of gold and a small dagger. You are awakened by one of your servants who tells you that your keep is under attack. You look out the window and see, and now we're going to enter this to the AI and let it generate a continuation for this story. So you look out the window and see orcs charging at you from all sides. The only thing that you can save you now is to take the dagger and kill them before they reach you. So what we're going to do is first we're going to change this to do mode, and we're going to tell it an action. So let's write, I pick up my dagger.
So we gave the input, you pick up your dagger and
the orc's charge is not enough for you. You swing your blade and cut down an orc with ease. You quickly run away from the battlefield, but then suddenly hear a voice calling to you. So now we're going to write, you turn around. No, you don't need the and. No. You turn around and face the voice. So this is our action, and let's see what the AI generates. It is a woman. She has long blonde hair and is very pretty, if somewhat cold looking. She carries no weapons that you can see, but she is wearing ornamental armor. Rise and shine. So with that, I'm going to leave it for you guys to play around with this. And what I want is I'm going to copy and paste this prompt so we all have the same starting point, and you'll be able to see that the network is really generating a new text. So I'm going to drop this prompt in the chat here. And what I want is for everybody to do just what we did, go to custom, type in this prompt, replace the insert your name with your own name, and follow along with the story. And what you'll see is that the network isn't just copying some pre-written text. It's actually generating this new text based on the context. And it's not perfect, but it does a pretty good job. So we'll give you guys about 5 minutes to play around with this. If you have any questions, feel free to post them in the chat. We'll be monitoring that. And the link to access this workshop will be, we're also posting it now.
change this.
Oh, sorry. I think we just sent it privately. Whoops. Can you paste all of it? Yeah. Yeah, so there's the prompt. Sorry about that. And here's the link to our website. And so we're going to give you guys 5 minutes to work on this now, but these websites are obviously openly available, and you can be sure to play with it more in your free time. But we'll just give you about 3 or 4 minutes now, and feel free to ask questions in the chat. So if you're having issues copying it, if you're having issues copying it, it's working from a computer, so maybe it's different on mobile or something. But if that doesn't work, feel free to type in any prompt that you want. It'll work with any story. But yeah, just Yeah, glad that you guys are enjoying it. This is actually, there's actually been even more improvements in natural language processing since AI Dungeon came out. This model here is using about, I think, 10 billion neurons, but the newest models these days have 100 billion, and they've seen a similar improvement in performance. So, it's pretty amazing what we're going to see. All right. So with that, if everyone could just wrap it up in about a minute, and we're gonna move on. And remember, like, if you didn't get enough time now, you guys can always play with these afterwards as well. All right.
All right, everybody. We hope you enjoyed the AI Dungeon. It's definitely really cool. But with that, let's get into reinforcement learning, which is another branch of artificial intelligence in an area of machine learning, where we try to train an agent to interact with its environment. So let's first take a look at how reinforcement learning compares to human learning. So let's say we're just a human and we're a child, and what we tend to learn through a few different ways. But reinforcement learning is really about how we have an agent, which could be a character of some form. For example, through this chart over here, we have a dinosaur, and our dinosaur is the agent. So the dinosaur is in this vast maze, and its goal is to find the tree so that it can eat some food. And what it has to do in order to get to that tree is it has to take actions. And our dinosaur is allowed to take 4 different actions. It can go up, right, down, or left. And at each step that the dinosaur takes, it can do 2 things. It can observe its state, which is the state that it's in. For example, oh, I'm in the right corner of the maze. And it can also observe its reward. So essentially, in reinforcement learning, what we do is we give our agent a reward for completing something. And this reward could be in the form of a punishment as well, where we give it a negative reward. So in this case, we might decide to give the dinosaur a negative reward for each step that it's not at the tree. And when it finally reaches the tree, it gets a reward of 1. So the dinosaur, or agent in this case, is incentivized to take actions in order to get to the tree. And over here on the left side, we have a similar thing where we're a dog in an environment, and the dog's goal is to try to get the stick so it can get rewarded, and it needs to take some actions. And you can quickly see how a simple task, like trying to get the dinosaur to cross around the maze, can evolve into something very complex, like training robots in real life.
And one important thing to note here is this is quite similar to how humans learn as well. And that's kind of the common theme of our presentation, which we want to show you guys, is that a lot of the advancements in neural networks, reinforcement learning, natural language processing are all based in advancements in how we understand how humans learn and how humans are able to complete tasks. So reinforcement learning is based on this idea of positive and negative reinforcement, which psychologists have sort of developed for humans. But now the question is, how do we encode this in a way that a machine can understand? So for that, we need some good old math. The way that reinforcement learning is kind of done in a more technical approach is reinforcement learning is about sequential decision making. So essentially, any problem where we have an agent and an environment and a goal can be defined as what are the sequence of decisions that I need to take, which will get me to the goal. And just like humans, there's kind of 2 major stages in which robots learn how to do this. The first is an exploration stage, and then there's an exploitation stage. So in the exploration stage, what the robot does is it takes random actions. So it will just try different things using random numbers and to figure out its next action. And what it does is, while it's doing random things, it keeps taking observations. So, in our previous example of the maze, let's say the dinosaur just randomly decides, oh, let me go down. Then it'll see, okay, I still didn't reach my reward, but my new state is that I'm closer to receiving it. So, okay, this was maybe something positive. Then it tries going left and it bumps into a wall. And it says, okay, that didn't work for some reason. I have no idea why, but going left here wasn't a good idea after I went down. So the way that this is kind of coded mathematically is we use something called a policy. So a policy is kind of a formalization of that decision-making process. Just like we have to make decisions in real life that, oh, do I want to, go to the restaurant that I always go to, or do I want to go to this new restaurant? A robot has to decide, okay, what are the sort of factors which lead me to making this decision? Maybe you think about, oh, what is my hunger level? What is my, what time of the day is it? All these different factors. So a policy kind of encodes that into math that, oh, if I've already taken 3 steps, give me a higher probability of going left. Like left for some reason seems to be better after 3 or 4 steps, or maybe going right is better when I'm closer to my reward. And so what reinforcement learning is all about is training that policy through these 2 stages of exploration and exploitation. And then the exploitation stage is when we kind of explore less. So we take less random actions and use the rewards that we've learned to try and take the better action. So for example, taking our previous dinosaur example again, say we've kind of learned that, okay, whenever I'm close to a wall, it's generally better for me to move towards a white space as opposed to hitting a wall. That's the policy that it's learned. And what the robot will do now, instead of just taking random actions, is it'll try to follow its policy. It'll still do some level of exploration. And the way that we define that mathematically is we give it a probability. So it has a probability of epsilon of taking a random action, and it has a probability of 1 minus epsilon of taking the smart action, the action that it's learned gets it closer to its reward. And the real benefit of this is, just like in real life, we need to explore in order to figure out the optimal problem. Like if our robot just immediately started applying its policy, perhaps it goes, it goes randomly for a little bit and it finds, oh, when I go down, that brings me closer to my reward. So the policy, if it just immediately starts applying what it's learned, it'll just be like, oh, let me just keep trying to go down, and it'll keep bumping into this wall and never reach its task. So we need some level of exploration to figure out what the optimal solution is, instead of just settling on the first policy that works. So the way that we kind of do this in a mathematical sense is something called Q-learning, which I'll go into in a bit more detail on this slide with another example.
Yeah, so this is the mountain car problem. And the mountain car problem essentially takes a car. And as you can see, the car is stuck on this very steep mountain. And if the car's starting position is around this point, and if it tries to directly just go up this little hill right here, it's not able to, because the engine of the car is not strong enough. So what it needs to learn to do is it actually needs to increase its momentum by going up the opposite hill and then going back over up and hopefully reach the top of the mountain. So our agent in this example is our car, and it's interacting in the environment, which is the mountain. So,
and more specifically, in the mountain, the car is getting certain information. That's its position and its velocity.
So as we said with the dinosaur example, it will take an observation about its environment. And as Aditya just said, the car will take the observation about its current position, which is its horizontal coordinate, and its current velocity. So then based on that, we can have our states, which are essentially those observations. It's observing its position and velocity.
And one important thing to note here is that in this problem, there's an infinite amount of states, right? You could have, because this is a continuous number, right? Your horizontal position could be anything from 0 to -5 to, +10. It's a continuous space. So technically there's an infinite number of possible states that you could be in.
Yeah, and then finally we have our actions, and our actions are simply the car can either go left, it can go right, or it can do nothing. So now let's just have a certain scenario. If we just go left the entire time, the car is trying to optimize its reward, its future reward, and that reward is obtained by reaching the flag. And for every step that it takes and not arriving at the flag, we give the car a negative reward. So over time, it will hopefully learn to reach the flag.
And the important thing to note here is that if we go left, even though the car is actually getting further away from its goal, we know that it needs to go left in order to eventually reach its maximum positive. Like if the car just, for example, keeps slamming the accelerator and goes right, yeah, it'll get closer, but it'll never get close enough to achieve the goal. It achieved partial of its goal, but it didn't reach the optimal solution. So again, this is why exploration is important. The car needs to try things that'll cause it to, get punished and lose reward, but that are eventually successful into reaching the optimal policy. So the way that we encode this mathematically is by setting up a Q table, which encompasses all of the future rewards that it gets. So that incentivizes the car to take longer term good actions. And the way that we do this is by essentially, like I said, just trying out different actions, measuring our reward in that state, figuring out if it got us closer to, and if our next step will get us closer to the reward, and adding those probabilities together. So over time, it developed this Q table, which is the list of all actions and all states that it can be in, and what it should do in each of those states to reach the reward. And the one important thing to note is this involves a discretization of the problem. Instead of looking at as an infinite number of states, we have to, reduce the number of steps. We have to reduce the number of states total to make it a solvable problem for a Q-learning type model. So that was a cool example of a mountain car. I'm going to shift gears a little bit and talk about a more complex example. So how many of you guys have heard about the prisoner's dilemma? Yeah, so the prisoner's dilemma is a kind of common thought experiment in psychology where we kind of say that, okay, you're a prisoner, right? And you and your partner have just been arrested for committing a big crime. Okay, and so now you're sitting at a desk, your partner's in a different room, and the officer comes to you and says, we have some evidence on you guys, but if you rat out your partner, I'll reduce your sentence to just 1 year. Okay, so if I rat out my sentence, if I rat out my partner, my sentence becomes 1 year, but my partner is going to get the full brunt of it. They're going to get 8 years of punishment. Okay, but then what the officer does is he goes into the other room and tells your partner the exact same thing, that if they rat you out, you'll get 8 years and they'll only get 1 year. So now, but what happens is if neither of you rat out each other, well, they don't have enough evidence to pin you guys completely on this problem. So you'll both just get 2 years in jail. But what happens is through game theory, we find out that the most likely scenario is actually that both partners will end up ratting each other out because the punishment of, getting 8 years while the other person gets off almost scot-free is too great to make it to make confessing the right strategy for both people, even though that ultimately results in both of them getting a worse reward. So this is kind of cooperation in a human example, but cooperation can also be used in games. Here's an example of a team of, professional capture the flag players. Not really, they're professional video gamers. And they're playing this game against actually AI agents. So what we found is that these complex ideas of cooperation can actually be solved just by this same idea of reward and punishment. These AI models were able to learn complex ideas of cooperation just by being given rewards and punishments, as we talked about in reinforcement learning. And these are some examples of that, like, the AI learned to sit in its opponent base to make sure that they couldn't get back to their base, to follow their teammate to protect them, and to defend their own base as well.
So where is reinforcement learning actually useful? Well, reinforcement learning can be applied to things like dogs, or not dogs, but robots.
Robot dogs.
Complex. Yeah, robot dogs. And that's best exemplified by the company Boston Dynamics. They've made a lot of military grade reinforcement learning based, robots. It can also be applied to self-driving cars. It can be applied to video games, not only just the capture the flag game, but even more complex ones, like, for example, Dota. And then it can be applied to classical games like chess, shogi, and Go. And what we've seen is that these reinforcement learning models are actually able to beat professional players, even when they're on teams. So this cooperation does exist, and the reinforcement learning models are able to learn that.
So now we're going to go into a workshop where you guys will be able to do this as well and actually get to code and play around with this mountain car problem that we talked about. So we're gonna start the demo for this, and with this one, we want you guys to do it at the same time. So if everyone could go to samyakscience.org/neurocon and open this up in their own tab, and we'll do this together so we can walk through it. Yeah.
And if you are restricted, in the case that you're not able to open it on your own as well, like based on your device, then you can also just follow along because we'll be demoing it via Zoom. So this is using something called Google COLAB. And what COLAB is it's basically a online notebook where we can run and execute this Python code. And this Google COLAB is often used for these artificial intelligence, like training and running these models because it's in the cloud. So what we're first going to do here is we're actually going to connect to the Google runtime. So this will just set up a quick virtual machine on Google server. And once we do that, let's get into our very first step. So here we're going to be doing, trying to solve the mountain car problem using Q learning, deep Q learning actually. And first off, we're just going to start by installing a ton of dependencies. And some of these are related to training our neural network, for example, using the torch library. We're also going to be creating a display so we can actually visualize the car moving to install, just in general for numbers, storing the numbers and the manipulation of those.
Yeah, so to run any code, you need to click on this little play button on the side of the window. So this code's pre-written for you guys and you just need to play it there. And once it's done loading, you'll be able to see that, it's installing some packages and things. So we'll keep moving.
Yeah, so while these are installing, I'm going to go ahead and explain the next step. So over here, we're using a built-in function, and it's called monitor. So the library that's behind all of this is something called Jain. And this is basically something that OpenAI has developed, which is actually the team that developed the model
for the capture the flag.
For the capture the flag game. And they're responsible for a lot of cool reinforcement learning development here. But essentially what this little block will do is it will create a wrapped environment and it uses their built-in monitor function. So monitor will automatically create videos of our executed car running. Next up, we have creating, yes, I'm just going to go ahead and run this.
And you can run things in sequence so it starts working while the last step is going on as well.
Yeah. So then next up, we're just going to initialize our environment by using the Jain and then also creating a path. So what we're going to do here is we're going to store some logs and then also set up the path for later when we're going to create our video files. So I'm just going to go ahead and run that. And what we're going to see here is it seems that our actual, our virtual machine was reset here. So what I'm going to do is I'm going to go to, so if you're following along with this, simply hit this, go to the file section, which has this little folder here, then go back and press this ... which will go back up a step. And if you're not able to follow along via the computer, you can just watch us demo it live here. Again, you can do that later after the workshop if you want to. We can create a new folder. We're going to create a new one in this directory called root, and we're just going to name that tboard logs. So this is required for the tensor board to essentially create some logs.
So now we're going to rerun this step.
Yeah, and then now it ran successfully. So next up, now let's get into the core of the reinforcement learning problem. So over here, we're just going to run some, this is basically running some random actions.
So what this is doing is we're first just looking at what would happen if the machine just took random actions. So what this code does is it sets up our environment. It tells it what the max position is. It sets up all the rewards. And it then creates these graphs. So what these graphs show is that we're letting the machine try just taking random actions hundreds of times, and then it'll generate a graph of how far that it got. And what you can see here is that over time, it just by taking random actions, it is sometimes able to hit the goal, but it never hits the goal, but sometimes it's able to leave, the starting point, but it never is able to actually hit the goal of the top of the mountain. And what, as I talked about, this is still an important step though, because what it does is it gives the machine information about what its environment is like, which it can later use in the exploit phase when it actually tries to learn this problem. So we're going to let that run. And in the meantime, we'll go into the next section about the policy.
So this basically defines our weights initialization. And what the weights are is that's earlier when we talked about the neural network. So we're going to use the Q-learning approach and also add a neural network with it. And so this is just initializing the weights. We're also going to create a class called policy. And that's just going to be around, our policy will have a few parameters, which is its state space, which is the actions and observations that it's taking. Another thing is a random.
So our random one just ran again, and you can see it's slightly different than last time because it is random action after all, but it was still never able to reach the top of the mountain. So 0 successful episodes. And so now what this policy does is this is just defining that, okay, this is the action space that we talked about. Like what are the set of actions it can take? What are the set of potential states using its position and velocity, and what is the model that we're defining, which is a deep Q learning model. So next, what we're doing is we're actually training that model. So in this code, what we're doing is the model is going through thousands of or hundreds of episodes where it's trying to apply what it learned in the random stage and improve it model further. So it's taking its policy, which it learned from the random stage, and applying that and trying to improve it. So you can see here that it's training over time. It should take about 2 minutes to do 500 episodes. And then we're going to look at how well it actually did.
Yeah, so while this is running, let's just explain this plot results right here. So as you guys can see, after around episode 330, the agent actually starts completing it. So over here on the y-axis, we have the position of the car. And at the beginning, it's moving a little bit away from its starting position, but it's not able to actually significantly get up the hill. But over here, we can see that it's able to get the negative position. So it's able to go left all the way up to the left portion of the hill and then go all the way right. And it starts to complete the problem. And after about episode 370, it's able to complete almost every single episode consistently with just a few outliers, as you can see here. So we're going to let that run as well. Our agent is almost done training. It just finished. And
you can see that it had 45% successful episodes. But again, that's after most of these, after about 370, it's doing it with about 100% success.
Okay, so now the next thing we're going to do is we're actually going to head back into our content, the folder, our directory, and look at our video. So as you guys can see, it generated a ton of videos, which include all of the various episodes here, and we can view these later. And again, we're running a little bit short on time, but here's briefly just a visualization of our policy, which is what our car was doing over time.
Yeah, so just to give a brief explanation of what this is here, this is this agent's actual policy. So that means this is how it's making its decisions. So what this says is that if the agent has any velocity that's below 0, it just keeps going left. So it keeps trying to go further left. And then once its velocity goes back to 0, it does nothing, which allows it to start sliding back down the hill. And finally, once it starts sliding with positive velocity, it slams rightward, which is the successful way of completing the task. And we would show you the video here. You guys can download these videos so you can see it once it finishes generating on your computer. But because of time, we're just going to move on with the presentation. So finally, we're just going to recap what we learned today. We kind of talked about 3 major branches of artificial intelligence. The first is neural networks. The second is natural language processing. And the third is reinforcement learning. And in each of these areas, we kind of talked about how it relates to the brain. Next, I want to talk to you guys about how we can move forward in this area. So one important thing to realize is that AI and neuroscience are literally driving each other forward. Advancements in one area is allowing us to make advancements in the other area, as this Nature title literally, kind of says it perfectly. One recent paper, which was pretty interesting, was they found that by taking unsupervised learning problems and inserting some noise representing a time for the AI to sleep during training, it was actually able to stabilize better. So that kind of shows how these advancements improve each other. And finally, you can see a new field called computational neuroscience, which is sort of built around this idea of how do we combine AI and neuroscience, which is a really interesting area if you're looking into, if you potentially want to make this your career even. Now, lastly, we want to talk about how you can sort of get involved in this area. 2 important resources are the DeepMind blog and the OpenAI blog. DeepMind and OpenAI are kind of leaders in this field. They're kind of respectively owned by bigger companies like Google and Tesla and those companies. But they've made a lot of the advancements that we kind of worked on in our workshops. And now, lastly, we're going to show you a few just super cool examples of what is the cutting edge of AI today. It's fine. So one of these examples right here, I can play this. If you like Bruno Mars, you'll love this example. But if you remember this famous song from Bruno Mars where he did this dance, they were actually able to teach an AI to convert a human video to represent that same dance. So these people here, the only video they took was of them doing this action here, and the AI actually converted it into the dance. And over here, when we talked about music earlier, here's an example of an AI-generated Bruno Mars song. You know, Bruno Mars is one of my favorite artists, so that's why both of the examples are his. But this is the song Uptown Funk here, and at first, this is just the normal song. So the AI was fed this portion of the song.
And then after a few seconds, it starts to generate by itself.
Right here. So as you can see, the song isn't totally perfect, but it's pretty amazing that the AI was able to come up with its own hook to this song through these ideas of natural language processing. And there's kind of this famous quote about how computers became a bicycle for the mind for humans, that it allowed us to take our own capabilities to the next level. And we kind of believe that AI will be this bicycle as well for students and for for humanity as a whole. So we think it's incredibly important for youth to get involved in this area. And our sort of vision and Samyak Science Society's vision of doing this is by combining these two principles of curiosity and experimental learning. You know, today we focused on some of the, technology aspects of AI, but we really wanted to give you guys a level of curiosity in this area. So that way you may be influenced to explore this on your own. And we did this through kind of like a hands-on approach and experimental learning. And we believe that through this approach, we can kind of motivate youth because, as they famously said, one Einstein was able to cause so much change. Imagine if we could have a generation with hundreds of thousands of Einsteins who are all interested in science, technology, engineering, and mathematics. So with that, we want to thank you guys for being here. Thanks for attending this presentation. It was really fun for us. We hope you guys learned a little bit as well. And this is just the tip of the iceberg. So I think that we're pretty much out of time, but we'll throw it back to our the NeuroCon representatives. And if you want to connect with us, feel free to connect on our social medias here or go to our website.
You know where I go when we're dancing. Handshakes and napkins and getting